Yes, let me try to now properly. Okay.
Yeah, don't worry. First of all, I'd like to thank already the attendees who are here. As you may notice, today is kind of a special seminar. To start with, the time is a bit earlier than usual, and as you have already noticed, it's going to be held in English. So please, if you don't feel so comfortable asking the question on the mic, you can type it down on the chat, and I will read it out to our speaker. And well, it's a pleasure for me today to introduce and present Andriana Makridou, who was a colleague of mine back in the Max Planck Institute. She's visiting also from the Ludwig Maximilians Universität. Both are there in Munich, Germany. She's a PhD candidate in the string theory department. And well, I know that she's an expert in the Swampland program, regardless of what she says. And she's so kind to give us today an introduction. So please, whenever you wish, go ahead.
Thanks a lot for the introduction, Julio. And it's great to receive this invitation and be here with you, at least virtually. So a disclaimer, this is some selected insights, so I will try to provide a more generic introduction, but necessarily I will give a bit more emphasis on some topics I've worked on. And I will also try to make it accessible for non-string theorists, even though this is my specialization. So excuse, please, my lack of knowledge in deep cosmological topics, but I will try to do my best. And please feel free to interrupt me at any point. Okay, I need to. All right. So just to bring everyone in the same page, first, let me explain what string model building is doing in very briefly. So the idea is that we start with some kind of higher dimensional theory. Usually we have supersymmetric superstring theories. These are 10-dimensional. We have these 5 so-called superstring theories. There is also M theory, which is the overlying, let's say, principle that is 11-dimensional. We can also have F theory that is 12-dimensional. And this, of course, is not compatible with observations, with an observable 4-dimensional universe. So we need to compactify. So then one selects your favorite manifold. Here, this is a sketch of the so-called Calabi-Yau, which are manifolds that have specific properties that are particularly favorable for string compactifications. Otherwise, you can have different manifolds like tori or Ricci-flat manifolds in general. And the idea is that the properties of these manifolds are parameterized by certain fields called moduli that are, for example, in the case of the torus, the radius of the torus, or how thick, let's say, the torus is. And these are effective fields in our 4D description, and these are a priori massless. So the idea is that we need to give a certain mass to these fields. This is called moduli stabilization. So we need to create this type of potential, scalar potential. Here I'm presenting just one field. This could be multiple. It could be higher dimensional scalar potential. And the idea is that we need to give some high enough mass to these fields that they are not detected, let's say, at our energies. And the way to do this is to include the ingredients like fluxes or brane or other string inspired or string predicted ingredients. And then we have this for the effective potential. We are studying the potential. And what one is calling string theory vacuum is these extreme points of the scalar potential. And of course, there are 2 different approaches, actually. Some people call vacuum only the minimum. While you can also see the approach that what is called vacuum is all extrema points. Yes, please.
Sorry, is this wishful thinking?
No, this is...
You have theories here with an enormous number of dimensions.
Mm-hmm.
Then you compactify, all right. Then you stabilize moduli this, and then you get to an effective 4D potential.
Mm-hmm.
That seems wishful thinking.
Well, you have concrete examples that you
from some richness to a scalar field.
Mm-hmm. It's indeed, it's not trivial. It's not a trivial procedure. And there was the need for the secondary revolution, let's say, to find a way to stabilize the potential and find that these fluxes are acceptable and admissible. And the thing is, you reach this potential. I'm sorry, there are some sirens. I hope you are not getting interrupted. The thing is, after you stabilize everything, then you need to go back and check what you have found. Is it an actual for the theory, or is there some kind of mixing between the higher dimensional relics, let's say, with a lower dimensional theory? Or there could be other problems, like this potential, maybe there is some instability in some direction, and this is not the true minimum. But a priori, let's say this is the idea. And also there are concrete examples, like you take a torus, T2 times T2 times T2, you compute, you get the potential, you compute whatever, you find it. It's not so abstract. It's abstract to say that you find the sitter. This is actually very, very hard, and this is highly contested, and I will reach this point. But at least for
Andriana, I had the same criticism towards your string theorist colleagues.
Okay.
And I stick to it.
Okay. Can I proceed?
Wishful thinking.
I see. Okay. I will proceed then, and I will say that what we conventionally one is calling a landscape is the set of all these vacua that can arise when one considers all possible Calambiau, all possible combinations of fluxes. And the initial idea in string phenomenology was that, okay, you have this huge number here, this huge estimate of how many vacua you have. And then the idea is, okay, standard model would be somewhere in there. And then you just need to find a strong enough algorithm to scan these billions and trillions and quadrillions of models. And then you will identify the model that has the correct gauge group and correct value of the scalar potential and so on and so forth. Now,
a small question. So in
yes.
This last statement, you're just focusing to the sitter vacua or both and the sitter as well?
Everything. In the number is everything that is giving some. And I will claim there that this number is an overestimation, actually.
All right.
So the main idea is that the Swampland project is coming to totally turn around this whole idea. And now we are saying that actually not all low energy effective field theories can be UV completed to quantum gravity. And here I will be using quantum gravity and string theory interchangeably, just because this is what I am working on. But in principle, this idea should hold more generally. And I will try to provide more generic arguments apart from string theory. So the idea is that we have this type of setup. And this parallel plane, you find this huge green, both light and dark green plane, let's say, which is the set of all good low effective field theories, like theories that have no anomalies, for example, or are normalizable, or would be whatever you require your theory to be a good theory. And then the idea is that actually only a very small subset of them can actually be UV completed to quantum gravity. So the initial idea was that everything can be UV completed to quantum gravity since we have so many choices, but now we are having the opposite approach. Quantum gravity is very restrictive, and now we should strive to figure out what this boundary is, what is telling apart the theories that are good theories of quantum gravity or effective theories of quantum gravity and those that are bad. And this is happening through the so-called Swampland conjecture.
Can you mention at least one example of UV complete quantum gravity?
One example of UV complete quantum gravity.
Because it's a very strong statement. Either not all, but there is one at least.
Well, you need to find the theory, well, string theory, but the low energy, probably some kind of supergravity, I would say, but concretely a theory on its own that is good, even 5 to the 4th, I would say, not so well, actually. So it's not that easy to find something.
Ricardo is right then. So it is wishful thinking.
Eloy, that's a low ball, eh?
From bottom up, it's hard, but you can go
in baseball terms.
Okay.
Well,
continue.
Okay, I start with our data. The data is, let's say, what I call string data, which is the data we have from all these compactifications that are giving specific effective field theories and whatever. I consider part of my data black hole physics and black hole arguments about black hole decay and holography. And all this evidence, let's say, points towards some kind of universal behavior. So this allows us to formulate specific conjectures regarding the conjecture. And then once you have a conjecture, the conjecture is in the form of quantitative statement like an inequality with specific coefficients or not so specific coefficients. The idea is first that you check it in theories that you know are good. So the sample of string theory compactifications, you think that there is no reason that they are problematic. They are just a compactification of type 2b supergravity on a Calabi-Yau. There is no reason where this can go wrong. It's like simple construction, or it should be like the Higgs potential, and the Higgs potential should pass the trivial test because it's something we want to have. And the idea is that maybe some of these tests are failing, so you need to go back and reformulate the conjecture in a specific way, or they might be okay, and then you're trying to find what are the cosmological consequences or phenomenological consequences, and so on and so forth. And also what is very important is that these conjectures are not random statements, but they are related to each other, and they provide mutual support to the whole building. So effectively what we have is some kind of web. There are these three cornerstone conjectures, at least in my opinion, which is the no global symmetries, the weak gravity and distance conjecture. And each of them is giving rise to several other sub-conjectures that are following, are related, other using additional assumptions, let's say black hole thermodynamics, or just extra assumptions about the good nature of the theory. So we have this no global symmetries conjecture, and I will also discuss the Coburn-Disch conjecture if I have time. There is the distance conjecture, and this is very much related with all these conjectures that are having to do with the type of vacua that are allowed. And we have weak gravity conjecture, which unfortunately I will not discuss so much apart from the main conjecture. But at the end of the talk, I will try to give an overview of what this web we are seeing here is all about. So let me start with a no global symmetries conjecture. This is saying that a quantum theory of gravity with a finite number of states does not admit any exact global symmetries. Now, the keyword here is exact. So this is saying that, okay, your low energy effective field theory might be breaking this global symmetry, but just marginally, so we don't really observe it. So in that sense, even though it's a very powerful statement and it's widely accepted already, like Wheeler probably was the first one stating this type of thing as an observation, it's not proven, of course, but it's not predictive when we look at our effective field theories, because we see, okay, we have some kind of global symmetry, but in principle, it can get marginally broken in high energies, and this is not saying much. However, what is the argument? Why are we claiming this? And there are two simple arguments. One, let's say, both of them are two cases of black hole evaporation. So we start with this kind of black hole. And now you have to make some kind of assumption. You start with a mass and a certain charge. Then you say that, okay, I let this black hole evaporate. Now this is not a gate charge, it's a global charge. So the horizon is not sensitive to it. So the particles that are emitted cannot carry this charge. So the final object that arises either has charge Q or doesn't have charge Q. So we have no conservation of charge. This is an inconsistent theory. Or it has charge Q. And at some point it has some mass, whatever, close to Planck mass, and where the black hole evaporation procedure will stop. And then we are saying, okay, this is a black hole remnant, and now people are claiming that remnants are bad. Of course, this is not 100% bulletproof. I have heard many arguments about why remnants are bad. The main argument is that you can play this game with any charge. So effectively, you have an infinite number of remnants, and then the infinite number of remnants will force the effective gravitational coupling to go to zero. So we'll decouple gravity, and this would be problematic. There are other arguments, even if there was an infinite number of remnants, we would observe them, and we don't, so they are not there. But I understand this is a kind of hand-wavy argument, but in any case, it's motivation enough to claim this conjecture. Similarly, we can have some kind of non-abelian case, an SU2 case here. So we have a black hole of charge A, and then we let it proceed. It evaporates. Again, the charge cannot change. And we are reaching a state that the mass is now so small that the area and the associated entropy is not enough to accommodate the dimensionality of the representation. So this would be a problem concerning the entropy. Again, another argument against global symmetries. What about weak gravity? the idea is that gravity is always the weakest force. Of course, the main motivation.
Andriana, sorry to interrupt you, but realistic black holes don't have any charge or less SU2 current. These are exercises.
Yes, this is an argument that is, let's say, you try to find a paradox, right?
You cannot use that as an argument because it's unrealistic.
Yes, I'm trying to say that if I start with such a black hole, I reach something that is not good. You're even saying that it's not realistic to have it. So, yeah, again, you're arguing that such an object should not exist. This is compatible.
A training as in astronomy.
Mm-hmm.
Never heard of
Also,
But how would you detect
even a
this?
star with a net charge.
Yes, but how would you detect it if it's not gauged? You can only detect it if it's gauged, because then you have the fake lines that come out and then
No,
they reach some
you're
kind of...
imagining things, you and your colleagues. It's okay. Keep going.
no,
Okay.
I have another observation. Even theoretically, the abelian case is allowed, but this is not the case of the no abelian case, because there are examples of highly abelian case, but they are unstable. So there is no example which is stable. So it is not realizable also.
But you're talking about global symmetries, not gauge symmetries.
No, ECU2. O sea, black holes with ECU2 hail.
Are there field lines going out?
A non-abelian hail. There is no stable examples.
Okay. So,
Which is
yes.
very different from the abelian case.
Example.
And also,
Yes, I'm not trying to claim that they exist. I'm trying to claim that if they existed, they would be problematic. Okay. So I think this is compatible with what you are saying. Okay, so the idea is that gravity is the weakest force. So we start with a theory, gravitational theory, with a U1 gauge field, just the action. And then the claim is that there must exist this specific particle that has mass and charge given by the following inequality. So effectively, the mass has to be smaller than the charge of the particle. And the reason is that extremely charged black holes should be able to decay. Again, do not have remnants. And the idea is that you start with the extremal black hole. You cannot have the most that you can have and keep being on the extremality line is some particle that is saturating the inequality. But if there is no particle that is having mass smaller than its charge, then this black hole could not decay because it would have to violate the extremality bound. So this would be problematic if you accept that remnants are problematic. And this also can be modulated and formulated into the magnetic weak gravity conjecture. And this is just happening by using electromagnetic duality. So one is just transforming, applying this thing, let's say, to a magnetic monopole. And one can use the relation between the electric and magnetic coupling. One is inverse of the other. And then we know that the mass of the magnetic monopole would be infinite, would be just all the flux in the universe if there is no cutoff in the theory. So one imposes some cutoff to have some kind of estimation for the mass, after which the magnetic monopole description is no longer valid. This is giving this mass in terms of the cutoff of the theory and the gates coupling. And plugging everything together, we get this inequality again. So the magnetic weak gravity conjecture provides a bound on the edge of validity of the theory. And you can also find the same value, let's say, of the threshold if you impose that this magnetic monopole is not a black hole. So the radius, the semi-classical radius is larger than the Schwarzschild radius that correspond to the monopole. Okay, and the third, let's say, basic conjecture is the so-called distance conjecture. And now we start again with a d-dimensional theory coupled to gravity. This is parameterized by this moduli space M. This would be, for example, the radion in the compactification on a circle when you compactify just one dimension. And here it's just the abstract higher dimensional. These are all scalar fields that are living on this moduli space. And then the distance conjecture is claiming that if you start from some specific point in the moduli space, you can always take an infinite distance limit where the distance between the two fields is different. So, for example, compactification to the circle just set the radius to infinity. And then what should happen is that one specific tower, an infinite tower of states, should appear with characteristic masses scaling exponentially, falling exponentially with the distance that is covered in this asymptotic limit. And this particular example is the one I was already mentioned. It's the Kaluza line compactification on a circle of radius r. The distance is logarithmic between the radius of the initial circle and the final circle. I just parameterize this as r because it's not really important, the actual points, but only the relative difference. And we see that the two infinite distance limits are 0 and infinity. And then the idea is that if you compactify just the usual field theory, you have the Kaluza line modes that are scaling as 1 over r. But when you have extended objects, like a string, you also get winding modes that arise by imposing that effectively the state when you go around the circle is the same, and this is imposing momentum quantization. And then you have this extra kind of states that is, instead of scaling like 1 over r, they are scaling like r. So no matter which limit you take, you always find the tower that is going to infinity exponentially fast. And this is a generic argument why you should have objects that are of extended spatial nature in your theory. Okay, and this is an example of a conjecture that can be, let's say, refined. And the idea is that here we are being a bit agnostic about what the nature of this tower is. We don't know where these are coming from. And this has been defined to the so-called emergent string conjecture. And the idea is that this nature of this infinite distance limits is dual. So either we have a theory that is decompactifying, so effectively new directions, spatial directions are opening up, and then the tower of states is the Kaluza line and these extra states, and then you need to take them into account. The cutoff of the theory because of the extra states is becoming lower, and this is effectively the higher dimensional Planck mass that is lower now. So our theory, the validity of the initial effective field theory is failing. In general, this is what distance conjecture is saying. You have infinitely many light states that you need to take into account. You cannot renormalize because they are infinite. So you need to say, my theory stopped being valid at some scale lower than what I started with. And the other option is that your theory, instead of having a decompactification, so extra space-time dimensions, you have an asymptotically tensionless Wakel-coupled string theory. And now you have the string theory that you need to take into account the higher excitation states, the whole spectrum of the thing, the string, and this is the infinite tower in this case. So this is providing a physical description, let's say, of the mechanism that is forcing this tower into existence. So these were the, let's say, the three basic parts of the Swampland program. And I would like to go and describe these more controversial, let's say, conjectures that have this more on-the-nose cosmological implications. So the idea is, and maybe the more controversial one, was the so-called de Sitter-Swampland conjecture, proposed by Vafa in 2018. And this, I have to admit, it was not very well founded. The idea was that we look at all the stringy examples, we cannot properly construct the sitter. We have some examples of the sitter, but they are not properly controlled. Or this has been debated, let's say. There is not a clear-cut opinion in the community. And so the claim was, okay, there is a way to quantify this. The easiest way to quantify this is to impose that the slope of the potential has to be larger than the potential itself. So this is automatically forbidding any kind of potential with positive value having any kind of extremum. And then reasoning, once again, is just lack of examples.
Sorry, a very ignorant question. This slope or this gradient is taken in what space, on the worksheet or on the embedding space?
No. This is the effective field theory for the moduli.
For the moduli.
So, yes, it's the moduli space. So usually it's some kind of n equals 1 supergravity potential or something like this, but moduli space. So with respect to the derivatives are with respect to moduli. And this has, okay, thank you. The clear implication that since there is no de Sitter extremum, this is...
Question.
Yes.
What is quantum gravity theory? Con potencial escalar. Esto no tengo idea.
Yes, indeed, we want to keep it generic. So it is some theory that is UV complete into quantum gravity and is described at low energies by this scalar potential, depending on these scalar fields that are moduli.
Entonces, es una teoría que me cuantiza el espacio-tiempo.
Sorry, can we switch to English?
Sorry. I'm giving classes. What is quantum gravity in this context? I don't understand. With a scalar potential?
Yes, for me,
even less. It's just absolutely mysterious. I'm familiar with I'm familiar with loop quantum gravity.
Okay, my starting point usually is, let's say, something like supergravity.
I'm familiar with supergravity that doesn't claim to be a quantum gravity theory.
Well, string theory does, and supergravity is claiming to be some specific well-controlled limit of supergravity that we have access to, and we can write down an effective action. And we are saying as long as this approximation is correct, we are at GS that is small, so at controlled string coupling, the higher curvature corrections are controlled, then supergravity...
But you give it as a fact, framework. That's the part.
Yes. I'm saying it's a conjecture, which is, it's not a theorem, it's a conjecture. So if we accept that it can be described by scalar potential, so there is some kind of theory that can be, but okay, I have no other experience. I don't know loop quantum gravity, let's say, but can you write down, how do you compute in loop quantum gravity, what background solution you have? Can you find de Sitter or Minkowski or anti-de Sitter? How do you quantify this? What I would say is a good quantum gravity description is a theory.
Please do.
Well, a theory that contains some kind of massless spin 2 tensor, which we can identify with a graviton. String theory has this thing. It's a quantized gravity that has no anomalies when transitioning from the classical to the quantum level. And I think for me, this is a good description of quantum gravity. So the 5 superstring theories, for me, it quantifies. I see the graviton, it is quantum, so it's quantum gravity. From after this, I cannot say anything more. And then I accept that there is this regime of...
Another question on the chat. Maybe I can read it. So it's about the nature of R. They're asking if this is the scalar or a tensor ratio.
Yes, scalar to tensor, yes. But it is restricted actually to be compatible with a conjecture. It has to be like very, very small, smaller than 0.07, if I recall correct what the number is. But the thing is, this conjecture has this order 1 constant that is undetermined, and there is a lot of work going into the direction of determining if we had a specific prediction for this constant, it would be easier to say what the experimental prediction would be, or the bound for the cosmological observables.
Thank you.
Okay. However, this is not allowing, it's not compatible with the Higgs potential. And this was the main motivation that this conjecture was reformulated. And now we have the refined de Sitter-Schoenling conjecture, which says that either the previous relation should exist, or now the minimum of the Hessian of the potential, so effectively the eigenvalues of some moduli have to be negative. So there is some kind of tachyonic description. So you can have a de Sitter extremum as long as it's not a maximum. And so the idea is that initially the initial conjecture was claiming that the only compatible vacuum would be an ADS or a Minkowski, marginally Minkowski case. But now the refined de Sitter conjecture is accepting also this kind of maxima as long as they are unstable enough. So the slope is stiff enough. But once again, we don't know what C prime is. So this is a bit unclear. And there is also the trans-Planckian sensor conjecture. This was a bit more physically motivated. So the idea was that sub-Lagrangian quantum fluctuations should remain quantum. So as the universe is expanding and stretching, let's say that lengths that are smaller than Planck lengths cannot become larger. They should freeze off before this happens. And this is putting a bound on the value of the Hubble parameter. It has to be smaller than 1 in Planck units at all times. And also now this can allow for the de Sitter vacuum that are maximum, as long as they are, the lifetime is bounded by the specific value. So we have this prediction, let's say, that is allowing for de Sitter, as long as it's short-lived enough. And actually in the original paper, they are comparing this to the lifetime of our universe, and they find it to be perfectly compatible. Also, they show that the specific conjecture in asymptotic regions of the moduli space, so let's say in this star-shaped thing here in these regions that I have indicated with black, so far enough where the field displacement is large, this conjecture is actually degenerating, let's say, into the de Sitter conjecture, and then it's becoming stricter. So effectively, as we look at this potential, this is saying that to the phi to infinity limit, then there we cannot find any de Sitter extremum. Okay. We also have some other ideas that are relating, postulating that de Sitter is not stable and has a finite lifetime, or it's providing bounds on the scalar potential. This one is the so-called no eternal inflation bound by Tom Rutelius, and he's just trying having a scalar field with a linear potential, and he was trying to solve the Fourier-Planck equation, and he found some constraints so that eternal inflation is not allowed, and he found the following bound. This is very reminiscent of the de Sitter conjecture, with the main difference that the fact that here the right-hand side is field dependent, potential dependent. And we see that in the case where d equals 2, so in two space-time dimensions, the two conjectures are becoming identical. And also this indeed prohibits de Sitter. And actually, it was also shown in this paper by these authors that this can give the same bounds as DCC when one has some nucleation of de Sitter bubbles. So there are this some kind of instantonic objects that have a specific value of the cosmological constant inside, and by nucleating bubbles, they decay into lower and lower and lower values of the cosmological constant, and this could be described by effective potential by a single field effective potential that satisfied the same bound as the one imposed by the DCC. And wait. There is also this different idea by Giat Valley, and this idea is that de Sitter is not a solution, but instead it's a coherent state over Minkowski, comprised of gravitons. And then the idea is that these gravitons, after some time, which is called the quantum break time, will start to interact with each other, and the initial semi-classical description ceases being valid. And this quantum break time is given by this following expression. And actually, when one assumes, again, a slow rolling potential, this is giving an expression bounds on the potential that are the same as the no internal inflation bound. So again, bounds that are similar to the de Sitter conjecture, but not the same. And we actually had some work related to that. And we made the observation that if you accept that there is some kind of thermal component related to this decoherence. So the effect that Valley is describing as quantum breaking can be viewed as the addition of a thermal component in the energy momentum tensor. And then you do a string study of this thing. So you compute the thermal partition function with a compactification Euclidean circle and so on and so forth. What you find is that in string theory, when you raise the temperature, no matter what the space-time dimension you have, you find a universal behavior and you find this contribution to the energy momentum tensor that is scaling like t squared, while in general it is t to the number of space-time dimensions. So effectively, your theory is becoming effectively two-dimensional. And this is exactly matching the expectation we would have from the no-eternal inflation bound to actually match the de Sitter conjecture bound. So it seems like this is some kind of asymptotic limit where this is again becoming strong enough to truly forbid de Sitter. Okay, so enough with this de Sitter business. The other type of vacua that are, let's say, relevant for the Swampland explorations are the ADS vacua, and these are in general considered nicer vacua in string theory. We have many examples, very well-controlled cases, compactifications that give infinite families of ADS vacua, and so on and so forth. So we start again with a quantum gravitational theory on an ADS space. So effectively, you start with this effective field theory description. It has the Ricci scalar, it has negative cosmological constant term, and it has this effective potential for these scalar fields, whatever they are. And now you're saying that there exists an infinite tower of states with a characteristic Mach scale, which appears when you go to the lambda to 0 limit. So they are claiming that the limit from Minkowski, from anti-de Sitter to Minkowski, is an infinite distance limit. And this is effectively a particular case of the distance conjecture appearing. So as in the distance conjecture, you have this infinite tower of states that is becoming exponentially light. Here, because of the logarithmic field distance, you have this tower that is becoming with a power law. Light in terms of the cosmological constant. Of course, it's exponential in the field distance. So they are claiming that you cannot smoothly deform an anti-de Sitter vacuum into Minkowski. And there is a strong version of this conjecture where it's claiming that for supersymmetric anti-de Sitter vacuum, this value of alpha here is 1/2. And this, once again, a simple example is just a type to be compactified on ADS5 crosses 5. In this case, there is a flux, 5-form flux that is supporting the solution, the S5 solution. And it turns out that this is forcing the radius of the S5 on the ADS5 to be the same. The Kaluza-Klein masses are scaling like 1 over the radius of the compact space, which turns out to be the same as the radius of the non-compact space. And this can be expressed in terms of the cosmological constant. So we have a direct verification of this expectation of the conjecture. And what is very important is this factor of 1/2, which is claiming that there is no scale separation. So effectively, there is no true supersymmetric for the ADS vacuum, because always the scale of the anti-de Sitter will effectively directly detect the modes that are arising in the compact manifold, the Kaluza-Klein modes that are living in the compact space. Okay. So this is a very recent idea that has very interesting consequences. And the idea is, where do we live in the moduli space? So let's say we have this moduli space of quantum gravity parameterized again by these scalar fields, assuming all this is possible. And then the observation is that we have so many parameters in our theory that are very close to 0, but not 0. We are claiming that this is Young-Mills Gates coupling. The value of the cosmological constant is extremely small, and something is forcing it to be extremely small. So there is this kind of cosmological hierarchy. There is this approximate B minus L global symmetry, or even close to exact B minus L global symmetry. So the idea is that since we have this moduli space, depending on where you are in the moduli space, these parameters will get fixed at specific value. And the closer you are to the moduli space, the larger these values are. But if you go to this absolute, let's say, asymptotic limit, you can indeed find some reasonable justification for having these extremely small values. And the main Swampland prediction, let's say, for this, is that you have this tower of light states that universally appears. So once again, assume we live in this asymptotic regime, and this is the reason that we have such a small value of the cosmological constant. What should happen? We should have an infinite tower of state that is appearing. This is scaling. The idea is this distance conjecture is scaling. Is claiming that this is scaling with in a power law relation with a cosmological constant. And let's generalize this to also positive potential. So not only anti-de Sitter, but de Sitter. No matter if you claim that de Sitter is possible, if it's de Sitter, quasi-de Sitter, some slow rolling potential, whatever. One makes the bold assumption to say, okay, let's generalize this and say that there exists this power law scaling of the potential with a mass of this tower of infinite tower of states. And one can actually find bounds on what this value of the power law factor is to respect the Higuchi bound, so no ghosts in the theory on de Sitter, or in the theory that is on positive cosmological constant background. C has to be larger than 2. And the other bound is that C is at most equals okay, this should have been the other bound.
Andriana, sorry, I have a daughter your age. Grab some water.
Yes, thank you. Thank you. So, okay, we are making this working assumption that is motivated by A, the Higuchi bound, and B, examples in string theory, that V scaling with is scaling with C bounded between 2 and the number of space-time dimensions. And what does this mean? If I can remind you the emergent string conjecture, when we have this extra time of space-time, this infinite tower, the origin of this tower is either this decompactification, which is saying that we need to consider extra space-time dimensions. And the cutoff of the theory is the new higher dimensional Planck scale, or we have this emergent string that is arising when the cutoff is the string scale. And the idea now, or the claim in this paper, was like, in reality, both these two options are decompactifications, because if you have this emergent string theory, all string theories are 10 or 11 dimensional. So effectively, you still go back to a 10-dimensional space. So you have these two options. When you have this infinite tower, you have two options. Either you decompactify in 4 plus n dimensions, or you decompactify to 10. And the idea is that this number of extra space-time dimension is bounded by experiments. And there are observational constraints depending on the size. So the size of the extra dimension can be, let's say, more constrained the more space-time dimensions we have. And it turns out that the only option we have is to impose that the scaling here is 4. Of course, we take as V the value of the cosmological constant we are imposing. This is giving a mass scale, and then we are this mass we are translating into some corresponding radius, and this radius is the one that one is comparing with experimental values. And we find out that this specific combination is marginally compatible. So the idea is that we have this single extra space-time dimension, which is saying that the size that it should have is of several micrometers. And the new fundamental energy scale can be computed, and it's 10 to the 10 GeV. And this is the whole idea of the dark dimension. So they are saying, if we assume the Swampland is correct, and if we additionally assume that our universe is in an asymptotic regime of the moduli space, then we have this very concrete prediction that is saying there should be a large extra dimension which is having the specific size. And now the fundamental energy scale, where this is becoming observable, is this new mass scale. And this is something that is experimentally testable, or at least the claims show in the paper, but this is not my specialization at all. But this should be something detectable in principle. And in our recent work, we tried to provide some kind of string realization of this. I gather you are not huge fans of string theory, so maybe I should not bore you with this. But the idea is that you have this kind of Calabi-Yau, where it is the standard type of compactification you have. And then you place this very long throat. You place this anti-D3 there, which will give a positive contribution to this n=1 scalar potential. We started with an ADS only having the bulk. Then you have the throat and the positive combination in the end. The throat has to be very long and highly warped so that the positive combination is highly redshifted, so we can balance out the exact value of the ADS vacuum. And then one is imposing that the total value of the positive now cosmological constant that will come out. So the de Sitter vacuum has a very small value. It's actually compatible with observations. And imposing this kind of relation, one can actually estimate what the scaling of the Kaluza-Klein modes in the throat is. And we find exactly this 1 to the 4th scaling, or V = m to the 4th. So we're providing some kind of explicit description of what would be a realization of such a dark dimension, let's say, theory. So it would be like the typical, let's say, type 2b compactification Calabi-Yau times a very long throat, which is something that is very well studied. And it's probably one of the best candidates that string theory has to provide some de Sitter example. Okay, so I finished with these, let's say, cosmological related conjectures. And I want to say a few words about the more mathematical part of my work. And this is the so-called cobordism conjecture. And this is a specific subcase of the no global symmetries. And to describe it, I first need to define what cobordism is. The idea is that we have two k-dimensional manifolds that are common, closed, and smooth, actually. M1 and M2, and one is saying that M1 and M2 are cobordant to each other if there exists a higher dimensional manifold at dimension k+1, such that M1 union M2 are its boundary. And now the way that this is becoming more interesting, to me at least, from diffeomorphisms, is that we now allow topology changes. And this is encoded into this Xi here. So we have this cobordism group. I will explain why this is a group. Omega k Xi, k is the space-time dimension of these manifolds. Xi is the structure, which is the additional restrictions we are imposing in our theory. And this, for example, could be just that our manifolds are admitting spinors. So you can have a theory with fermions. So this is a usual, say, first assumption. And this is a group because we are, the group operation is now the disjoint union. And we are defining these equivalence classes under cobordism. The empty set is the identity element for this operation. And of course, we have the inverse element. And if we don't impose any additional constraints, one can formulate this, take two copies of the same manifold, then it's clear that they are the boundaries of this tube that has these two copies of the manifold at the end. So it's clear that this is cobordant to 0 and then can be vanishing and can be shrunk into nothing. Okay, and then if you impose additional things, then you need to be a bit more careful on how you make this, how you define this operation. For example, if you have orientation, then you need to add the disjoint union of the orientation reversed manifold. And how is this now relevant for quantum gravity, let's say? So we start again with a d-dimensional theory, and then we compactify this theory down to d minus k dimensions. And we get EFT1 here, EFT2 by compactifying on the second manifold, and there is some domain wall interpolating between these two theories. So it means that when these two manifolds are cobordant to each other, then we have a finite energy transition between these effective field theories. Okay, so we have this cobordism group. This cobordism group is related to specific cobordism invariants. These are just maps from the group to Z or Z2 or some other abelian group. And of course, I should say that the cobordism group is always abelian because there is no way to define ordering in this disjoint union. And these invariants are always trivial for the empty set and the whole equivalence class of the empty set. So all the null Born manifolds that are boundaries of these higher dimensional manifolds. But of course, if they are not in the null equivalence class, then these cobordism invariants are non-zero, and then we have some abstraction of this manifold to decay into nothing. So this non-vanishing cobordism group corresponds to the d-1 minus k dimensional global symmetry, with charges labeled by these classes. And the idea is, again, there are no global symmetries in quantum gravity, so one can formulate the cobordism conjecture. And now the cobordism conjecture is stating that all cobordism classes in the theory of quantum gravity should be trivial. And this is encoded in this structure here. So what I call here QG is the structure of quantum gravity. So it means that when one is taking into account properly what the theory of quantum gravity is, all the effective field theory description of this theory should be related to each other. So we see here, we have this previous setup, but now this is null burdened. So we have EFT1, domain wall, EFT2, domain wall, and now this is leading to nothing. So there is no effective field theory that is arising by compactifying on nothing. So there is some domain wall, which is an end of the world object that is kind of eating up this effective field theory. And oops, this should have been already there. And the major application of this, and this was the initial motivation that they were formulating this, is that there is a single theory of quantum gravity. So all theories of the quantum gravity should belong in the same trivial cobordism class. And the idea was, for example, okay, in string theory, we have these dualities between type 2A, type 2B, which one is more fundamental? And then the idea is I have type 2A, I compactify on some manifold, I have type 2B, I compactify on some different manifolds. These two manifolds must be cobordant to each other and cobordant to zero when I'm taking the full theory into account and not just an approximation that might be crude or missing specific ingredients. And the main problem is that, of course, we don't know what the proper structure of quantum gravity is. So we start with some kind of crude approximation. This, as I said, could be spin or spin C, which means that we have charged fermions in the theory. This has group elements that are non-vanishing. And then the idea is we have this global symmetry, and then we need to treat this global symmetry. And the ways of treating the global symmetry is either breaking, which means to add explicit objects that are breaking the symmetry, or gauging. And for gauging, I will not have time to discuss much, but the idea is that effectively, even though that the whole group is not vanishing, you pick the equivalence class of the whole non-vanishing group that is zero, and the mechanism that is forcing you to pick this vanishing cobordism class, the trivial cobordism class, is the gauge fields that you have not included in your quantum gravity description, the structure, let's say, approximation you had. And the fact that this is trivial is effectively reminiscent of the fact that the gauge charge over a compact manifold should, the integral should vanish. And what is even more accessible on the nose, let's say, is what is the breaking mechanism. And the idea is that you start with this group that is non-vanishing, and the problem is that you are missing some fundamental ingredient of your theory, some object that should be there. And you start, let's say, with this manifold here that is not the boundary of anything, but you have forgot some kind of defect that if you include, then you are able to cap off the space-time and trivialize the group. And we actually try to provide a specific example of this. So there is one associated idea. These are the so-called dynamical touch poles. These touch poles are potentials effectively that are not exhibiting any kind of extremum. Usually they are of exponential form, and this type of potentials are arising naturally in supersymmetry breaking setups. For example, in non-supersymmetric type 1 theory. And there are many examples. These are very well studied examples. And the idea is that contrary to the usual touch poles, these are not indicating some kind of fundamental inconsistency of the theory, but they are just saying that you're not trying to solve, there is no maximally symmetric solution, or that would be the extreme one, and you need to look for a solution with a lower degree of symmetry. And now this has been reinterpreted in terms of cobordism by the Madrid group. And the idea is that actually this was an observation that in these cases that we have this dipole potential, there are these lower solutions of a lower degree of symmetry that have space-time finite distance. This is some kind of spontaneous compactification, or it could mean that there are some singularities in the space-time solution and they are not letting you proceed further, and so on and so forth. And what they are claiming is that this apparent singularity is that the fact that in reality your theory is containing an object there should be a cobordism defect that is located there and is giving rise to the singularity. So this is not an inconsistency of the theory, but it's a fundamental object that should be there in order to cap off some kind of space-time dimension. And they are claiming that when this is happening, there is also the specific scaling behavior. So the space-time distance is related to this field distance, and also the Ricci curvature. And this schematically is shown here. So we have this dark green line. This is the space-time solution where the circle is the singularity. This is parameterized by this field that is going off to infinity. And the fact that it's going off to infinity is showing us that we have this end of the world brane. So space-time is finishing there, and you have some kind of smaller number of space-time dimensions in the lower symmetric solution. And we provided an explicit example of this. So there was this kind of solution. The exact details or where it's coming from don't really matter. For string theory, it's a very well motivated type of object. So it's either a non-BPS D8 plane or a stack of anti-D8 planes and orientable planes. We have this effective field theory description. It's a dilaton gravity description. We make an ansatz for solving the equation of motion. We find solutions. We have two types of solution, the so-called solution one and solution, the pair of solutions that is called plus minus here. And the exact details are not important here. But the idea is that we have this radial direction, which is the transverse direction to the 9-dimensional object we started with, which only has trigonometric dependence in the solution. So this is actually a compactification on a circle. And this is actually behaving, showing singularities in the specific values of the radius, where the string coupling is diverging. So this is the prime setup that I was describing before in the dynamical cobordism. We have the solution that has some kind of singularities. Hopefully this is at finite distance so that everything applies. And then this should be signaling that there is some kind of cobordism defect there. And just to show the picture, let's say, this is the warp factor that I'm designing here to the left. And to the right, you see that this is the r direction. At r equals 0, this is where we have placed our 9-dimensional object. And here we have the spontaneous compactification in the r direction. And we see that exactly at the opposite side of the circle, this is where we have this logarithmic singularity appearing and the strong Hamilton regime. And the idea is that we have now this y direction, and the proper space-time distance between y equals minus infinity and plus infinity, depending on the solution, can be either infinite or finite. And the solution to plus actually turns out that it is finite. And there we can try to apply the dynamical cobordism setup and try to find space-time solutions that are reproducing the singularities we have. So what is our input? The input is we need an 8-dimensional defect. Why do we need an 8-dimensional defect? Because we have an S1 direction that is being capped off. We have this circle. This is a compact 1-dimensional object. This means that our cobordism group omega-1 is non-vanishing. And this means that we need a 10-1 dimensional object. So we make some ansatz for the metric for this. We know that we need to preserve now the symmetry along this 8-dimensional object. And we have these two directions that need to be non-isotropic because the solution we have already is non-isotropic in these last 2 dimensions. So we make the following ansatz for the metric. And we actually find a pair of solutions. And I want to say that the qualitative behavior is exactly what one would expect. So we have these logarithmic singularities at rho equals 0. We can show that the cobordism relations are verified with the exact same scaling. So this is not a coincidence, it's the exact same numerical value that is arising also in the previous solution. And qualitatively, I just want to show this diagram. So these two are the two solutions we have. I'm showing here the warp factor. And what I'm showing is that there is one radial direction. This is a polar plot. So there is one radial direction in each of the solutions where space-time, the metric is shrinking into 0. This is in minus pi over 2 and plus pi over 2, while we have this opposite direction, which is towards the center of the solution, so towards here. And
Sorry,
this is showing...
Andriana,
Yes.
it so happens that my background is in general relativity. This reminds me a lot of the Zezeker solution in general
I'm not aware of it, but please go ahead.
Zezeker, S-Z-E-K-E-R-E-S.
Yes. Okay.
Which is a non-isotropic solution in general.
In how many dimensions?
In 4.
In 4.
Well, in my undergraduate thesis, I generalized to 5.
And what is
it's exactly the same setup.
That would be very interesting, and it would be very interesting to see if there is a non-combining solution that is of one direction more, let's say, that would correspond to that.
I thought it would be useful.
No, that's a very good point, and the first time I hear of this because I have no GR background. And thanks a lot. I will look it up.
No.
Thank you. And what I was saying, okay, that here we see exactly that the warp factor is disappearing in this direction. So we have exactly what we are expecting by cobordism. So space-time dimensions being cut off, while the other direction has infinite length. And it's reproducing the singularities. So the idea is that the initial solution was not a problematic solution, as was initially believed, because this first type of solutions was already found by Dudas and Murad in 2000. But actually was a solution that was missing this cobordism defect that we are explicitly describing here. And we were the first ones that had some explicit description of the accompanying defect. And I think it's really goes beyond the coincidence, because we have the cobordism interpretation, the dimensions all match, the scaling behavior is matching. Everything is turning out to be very consistent. It was not trivial at all to identify the solutions fulfilling all these conditions. And the interesting thing is that in string frame, this coupling of this solution to the graviton is different than the usual D-dimensional DP branes and so on and so forth. So it seems like this is a new object in string theory that was not detected before. And now with cobordism, we had the option to access it, let's say. And of course, it would be very interesting if one could find an explicit CFT description of this and study also the stability and other secondary, let's say, issues related to this solution. Okay. So I think this is all I had to say. I think I'm already almost running over time, but I started with this, let's say, Swampland web. I hope I tried to give you the main idea about half of it. Of course, it's a very, very rich project. So I would like to conclude with my next slide, which is that quantum gravity is imposing serious constraints in low energy theories. The Swampland constraints conjectures are providing a solid way to probe what this universal behavior is. The interrelations between the conjectures are providing support and show that probably there is some common underlying structure. And these are not random conjectures that one is making, but there is some kind of physics lore behind all of this. And actually, testing and challenging conjecture is something that is very useful for giving very useful lessons for quantum gravity itself. Here, I mean string theory. And for example, let's say we have the de Sitter conjecture, but we have examples of de Sitter constructions in string theory. But once we saw, okay, we don't really expect to find de Sitter, so why are we finding it? People started identifying problems in the control, let's say, of these string theoretical solutions. So it was a very useful tool to identify the places where our model building was a bit weak and what we have to do better. And the last part is that Swampland ideas do have observable signatures. So it would be very interesting to look forward to that and see if actually something of this gets confirmed or even rejected. I think would be equally exciting. Thanks a lot.
No, thank you, Andriana. It was really interesting. I know that you're a bit tired from the throat. Is it okay to open for a couple of questions, maybe?
Yes, please.
Yes? Okay, so I encourage in particular to the students, if they want to ask any questions.
I don't know. I cannot see the chat, if there is something in the chat.
Let's see. No, apparently there is nothing else, nothing more. All right, maybe I can start with a question. So if I understood correctly about this coverdism conjecture, if it happens to be true, then there is a single unique theory of quantum gravity, right? And
yes.
This also holds for the effective field theories, which means that they would be connected through some sort of duality, or is it?
Yes, this was the idea. It's not clear to me at all how this is happening because we are missing this true quantum gravity structure. But I think this was one of the main motivations because let's say you have type 2A and type 2B and you have T-duality or you have S-duality between string theories. But everything is relating the relations, let's say the string theories in pairs. And they're saying, okay, but we know that there is a deeper structure between the 5 superstring theories and there is M theory. How do we see this in a deeper way, let's say? And yes, so the idea is that all of them should be related once we identify the full setup.
I see. Thanks.
Sorry, but string theory promised us a unique theory that included gravity long time ago. We are talking about 30 years. Then there was a revolution, then another revolution, and then I don't know, I lost count. In Mexico, the joke would be una cuarta transformación.
The fourth.
And I don't really see. Sorry, I comment from my friendship with Jean Justin. Is that in string theory is a lot of conjecture and very little solid research.
Well, I kind of disagree on that. I mean, of course, there are...
Oh, of course you disagree with it. You're in the business.
It depends. First of all,
I'm telling you, there is in the string theory is the inheritor of quantum field theory.
In what sense?
Of quantum field theory, that at this time was considered a mathematical entertainment until it proved itself in the accelerators. And string theory is, in my mind, at the moment, not passing the test. But
not proving itself. Well, I don't know. There are so many things that are self-consistent in string theory, so many non-trivial tests you can do. And it's passing the mathematical tests. It's predicting mathematical structures that have not been exploited by mathematicians yet. And to me, this is
what you said about cobordism seemed absolutely intriguing.
Yes, it's a recent idea, but it's actually, and we are doing a lot of work finding a bottom-up description of string theory. And this goes towards the direction of gauging. And I don't know if you are familiar with K-theory.
Yep. And
Yes.
cobordism, but I never thought it had any application.
Yes, actually, we are trying to find, there are the so-called tadpole constraints in string theory, that usually they are arising, you have the compactification, you have this Calabi-Yau, you find this genus, and you have to play by the contributions of the localized the branes and the fluxes, and so they need to balance the genus of the manifold.
But then you still have 10 to the 180 backward to contend.
But they must be cobordant to each other, right? This is the idea, or the theory that is giving them. The theory is
trying to show light.
Yes, exactly. And we are trying to sharpen the conjecture. Yes, we are trying to sharpen the conjectures, because right now, if you see, there are many conjectures that have these numerical factors of order 1. And okay, if you have this thing and then you find 10 and you say, order 1, fine, then you cannot have a very restrictive prediction or a very restrictive set of vacuum. But if you say that this constant I have here has to be 0.8 and this is it, and if it's not, I exclude the solution, I throw it away, then it's a much more restrictive setup. And there are also more mathematical ideas. There is Thomas Grimm.
Sorry, I have to quote you back, my friend Jean. Sin Justin autor de Quantum Field Theory en Critical Phenomena, que probablemente tienes. Sorry, I'm switching to Spanish.
Yeah.
Jean was criticizing string theory for being too many conjectures. Not even in mathematics, you have a few isolated ones.
Yes, but the idea is that actually they are not many. They are very few. And one is just producing the other, and one of them is just a reformulation of the same basic principle. And actually, one could claim that if you accept that no global symmetries happen, then the cobordism conjecture is immediately following. And then you have the cobordism conjecture, and then you can already build the tadpoles of string theory without thinking about compactifications at all, which is a really bottom-up approach. And it's one principle that is giving you tadpoles for all the theories. And this is something we are working currently on, and we are trying to identify.
That's the one thing where I believe you. With my background in general relativity, global symmetries are associated with global symmetries. General relativity has none. And so,
what is the reasoning in GR for this? Is it just observation, or is there a fundamental reason?
The gauge group of general relativity is the diffeomorphism group. It is not like the Poincaré group. No translations, no rotations, except locally. So that I buy without a doubt.
That's good then, because then you automatically kind of buy the magnetic weak gravity conjecture. Because can I go back and show? Where is it? Okay. I'm a bit slow, I'm sorry. Okay. 1 second, my laptop is struggling a bit. But what I wanted to say is that, for example, you have this magnetic weak gravity conjecture, and you say that the cutoff of the theory is bounded by this Gates coupling constant. But sending this Gates coupling to 0 is effectively transforming the Gates coupling, the Gates symmetry into a global symmetry. And this, based on the no global symmetries, is something prohibited. And this is extremely consistent here because it's saying effectively that the cutoff of the theory should be nothing. So the theory is not consistent at all. So the moment you impose that your theory has a global symmetry, already the weak gravity conjecture now at this point is saying that the theory is problematic. So in the sense, they are related. It's not like they are independent conjectures and they have nothing to do with each other and we are putting out a thing and another thing. It's really connected. And the structure should be one thing behind all this. And there are attempts at trying to explain it.
I admit it's interesting. I do not think is realistic.
Well, I mean, interesting is already improvement, I think.
But that's my modest opinion. I don't. Yeah, thank you for your excellent talk.
Thanks a lot. I'm happy you found it interesting.
Thanks.
And so sorry for interrupting you so often.
No, it's good to be. They were tough questions, I have to admit, because usually I'm only speaking to string theorists, and it's nice to have a different perspective from people that have different backgrounds, because we take some things for granted, and it's yeah, maybe we shouldn't.
All right, thank you. Maybe I insist in a further question from the students, if there's any. Or in general, whoever wants. They're shy.
On a personal note, Andriana, I have a Greek brother-in-law.
Ah, from where?
From Athens.
Well, statistically, it was likely.
Sure enough. All right, I guess this would be fine. Thank you very much for the effort. I hope you recover completely soon. Thanks
a lot. It was really nice giving the talk. And if you have further questions, please don't hesitate to reach out, and I would be happy to discuss more. And
yeah,
bye-bye.
Thank you very much. Also, always welcome here to the University of Veracruz.
Oh, that's a very serious.
Yeah. All right. Thanks a lot.
I appreciate your time to participate with us.
Actually. Bye.
Right.